we need matter fluid. And
Go ahead.
okay, so for inflation, we need some special kind of matter fluid. Specifically, we need a scalar field. I'll come to it. But anyway, so after this inflation happened, is it start?
Yeah.
Can I go to?
Yeah.
No, it's cannot be done. Okay.
Let's wait for a second.
Okay. So basically, we have inflation. Oh, we have inflation. After that, the universe enters a radiation dominated era. Radiation dominated, what is radiation dominated? Because at that time, the temperature of the universe was so high that all the matters in the universe one can treat relativistically. When can you treat matter relativistically? When the temperature of the particle is much, much higher than the rest mass of the particle. Okay, so you can understand if the universe is very, very hot, whatever constituents were there inside it, their mass was much, much smaller than the temperature. So all the particles were very relativistic in nature, and that's why you can basically treat all that cosmic fluid as a radiation fluid. Okay, and once radiation and of course the universe is expanding, and with expansion, if you expand something, it will cool down. So it's cooling down, and the temperature, with the expansion, the temperature also drops. So here you can see these energies. You may not be able to read it very nicely. Energy is equivalent to temperature. The energy is reducing, and at some point of time, what happens that the temperature is so low that now you can start treating your matter as non-relativistic particles. And that era I'll call as matter-dominated era. Something very important happened in this matter-dominated era is this formation of cosmic microwave background. Cosmic microwave background is a very interesting thing that happened during matter-dominated era. What happened is that all the photons in the cosmic plasma got decoupled from the rest of the plasma. And this is the bath of photons which will not interact with any other matter in the universe. And they are, since this period, it's streaming towards us. This is today, but we are here and we are looking back in time. And all these cosmic photons, which were before that, it were very tightly coupled with the matter in the universe. It was interacting with the matter of the universe. But then it got decoupled. Why it got decoupled? Because at that temperature, one could form neutral hydrogen atom. Because there is proton, there is electron. They can come together, they can form hydrogen atom. But if the temperature is very high of the bath, there are photons whose temperature is very high. And you know the binding energy of hydrogen atom is 13.6 electron volts. If the temperature of the photon in the cosmic bath is higher than 13.6 electron volts, then a photon can come and knock out that electron, can provide enough energy which is greater than binding energy and can knock that electron off. And then you will again get a proton and an electron. Okay. Unless and until all the photons in the cosmic plasma has gone down much, much below. So here Shah ionization formula is very important. It doesn't happen at exactly 13.6 electron volts because it has a tail. There are lots of photons in the tail which has much energy in the more than 13.6 electrons. So it takes some time. And when most of the electrons are much below 13.6 electron volt, then all the protons and electrons can come together and form neutral hydrogen. And once it forms neutral hydrogen, there's no electromagnetic charge left in the universe through which the photon can interact. So the photon got decoupled from the matter. And then since then, we are observing all these photons here in the microwave range today. That's why when it got decoupled, it was not in the microwave range. It is more cosmic microwave background because today we are receiving these photons in the microwave region. So we call this cosmic microwave radiation. Why it is important? Because before that, these photons were very tightly coupled with the universe, with the rest of the matter. So whatever imprints these earlier epochs might have can get imprinted on this photon bath. And once you detect this photon bath, you detect these different features, you can go back and infer what had happened before this photon bath got decoupled. even so, this photon bath got created when the age of the universe was 3,80,000 years. But it can predict what had happened when the age of the universe was 10 to the power minus 30 seconds. Okay. So that is why it is so important that even it happened much later than inflation, it gets the inflationary imprints can get imprinted on the CMB background. And once we detect the CMB, we can infer what might have happened during inflation. Okay, so that's why it is very important. And after the matter dominated era, we have again entered an accelerated phase. We know that we now in a dark energy dominated era, but we are not going into that. Okay, the CMB has got all the Nobel Prizes in cosmology except one. One has gone to dark energy, but the first detection of CMB was by Penzias and Wilson. They were not trying to detect CMB, they detected it by accident. They received a Nobel Prize in 1978, and they saw a very uniform temperature of photons coming from all over the sky. The temperature is 2.73 Kelvin. So you can understand how cool it is. Okay? And Kobe in 1992, they detected that not only this photon temperature is very uniform, it has fluctuations over this uniform temperature of the order of 10 raised to power minus 5. So if the temperature is in kelvins, these fluctuations are of the order of 10 raised to power minus 5 kelvins. Okay, so this is Kobe, which first detected it. Then WMAP confirmed that these fluctuations are real. Again, they looked at the CMB sky and had mapped these fluctuations. And once WMAP confirmed it, Kobe guys got Nobel Prize in 2006. WMAP detected polarization on top of that. WMAP showed that not only these photons have some temperature, it also, these are all polarized. But for semi-polarization, there has not been yet any Nobel Prize. And after WMAP, we also had another more precise experiment, satellite called Planck, which was an European collaboration. So you can see this is that anisotropy background which Kobe had probed, and this is the WMAP, and this is the Planck. You can see the precision, how precisely. Now we really know the Planck's sky. Through Planck, we know this sky very precisely, the CMB sky. Okay. And as I said that WMAP detected that it not only has temperature, it also has polarizations. If the polarization patterns are mirror-like, which are mirror image of each other, we call that as E mode. And if they are not anti-mirror-like, then we call them as B modes. And this is the CMB background. If you plot it, the CMB photons, in the frequency, you will just get a black body spectrum. This is probably and these dots are actually error bars. And you can see how precisely measured black body spectrum it is. What black body spectrum tells us that there were thermal equilibrium. So it means that before the CMB photons got decoupled, it was in perfect thermal equilibrium with the cosmic plasma. So this is a guaranteed thing that the cosmic micro background was in thermal equilibrium. And this is this. So we are seeing this fluctuation, but how do we measure them? We measure them as 2-point correlation function. What is 2-point correlation? So there is a fluctuation on this part, there is a fluctuation on this part. How much this part fluctuation is related to this part? You can make statistical correlations. Okay. And this 2-point correlation function, you are mapping on a spherical sky. So on spherical sky, if you have to map it through spherical multipoles. So these are these multipoles, L, and these are the amplitudes. So this is how the fluctuations, the 10 to the power minus 5 order Kelvin fluctuations would look like if you plot it as a function of multipoles, on spherical multipoles, on the CMB slide. And this red curve, which I have done, is a theoretical prediction from inflation. So inflation has said that if there is something like inflation had happened, then the CMB spectrum would look like this. Okay, so this is a triumph of inflation, and you can see how forget about this very lower L few lines, but on higher L, it has a perfect match. Okay. And all these dots comes with error bar. These are not just dots. So you can see how precise these points are. And if you want to plot the temperature and polarization on the same plot, this is how it would look like. So this is this temperature, this is this plot. But as because now I want to plot polarization as well, so the scale has got squeezed, so that this whole spectrum is squeezed into this whole branch. This is the temperature E cross correlation. This is E mode cross correlation. And this is B mode cross correlation. Okay. There is no E mode, B mode cross correlation, and there is a reason for symmetry. If you want to know, I'll later tell you why there is no E mode, B mode cross correlation. Okay. But let's talk about inflation. Enough of CMB. So why I have said so much about CMB, just to show you that inflation is not something which has nothing to do with observation. Anything you do during an inflationary era can be cross-checked with the present data. Okay, so it's a theory. It's of course a theory. It's actually a paradigm. There is no one theory which explains inflation. There is a paradigm. There are many theories. But the thing is that the good part is that there is also observational data, and you can go and cross-check your inflationary model. Okay. Okay. So if you have to do cosmology, you have to do general theory of relativity, and the guy is Einstein. And this is not because I'm against smoking. Of course, I'm against smoking. But this is also our government mandate. You cannot show publicly smoking or drinking or anything. So if you show something, you have to drink it. Yes. That's why you cannot.
Last time I said that the glasses all have water.
Anyway. Okay, so as I said, so inflation is a very brief epoch in the early universe when the universe had expanded exponentially. Of course, the dynamics is governed by Einstein's field equation, and I hope all of you have seen this general theory of relativity equation, G mu is equal to T mu. What this theory tells us, G mu you can determine by the space-time metric. So the left-hand side tells us how the background is evolving. And the right-hand side tells us how the matter is evolving. This is the energy stress energy momentum tensor, right? So left hand tells us how the geometry is evolving, right hand side is telling us how the matter is evolving. Einstein says that these two evolutions are coupled. So if the geometry is evolving in such a way, it can perturb the test particles, and if there are matter which can actually curve the space-time, then its dynamic will change the geometry of the space-time. Okay, so this is the physics behind Einstein field equation, that both the evolution of geometry and matter are coupled. Okay, so and the geometry in cosmology is the Friedmann-Robertson-Walker metric. Friedmann-Robertson-Walker metric in Cartesian Cartesian coordinates looks exactly like Minkowski, except one factor. And that factor is sitting in front of the spatial part. And you can see this factor also depends on time. That means the space part, not the time part. The space part has a time evolution thing. It tells you either it can expand or it can contract. How do we know we are in an expanding universe? Thanks to Hubble. Before that, no one could tell whether we are in an expanding universe or in a contracting universe. So from Hubble experiment, we know that we are in an expanding universe. And during inflation, this is called a scale factor. And during inflation, this scale factor is exponential. This h is a constant, integration constant. It is called the Hubble parameter. And this is almost constant. Why I say almost constant, I'll just tell you. What happens if it's perfectly constant? There is a problem. And then you can have inflation, but then as I said, no normal matter can give you accelerated expansion because normal matter will gravitate. So if there is normal matter, it will always decelerate the expansion rate. Okay, so you need something exotic for the universe to expand exponentially. Okay, and then it was shown in 1980 by Alan Guth and Starobinsky and many other people that if you can have a very simple scalar field, which is a function of time alone, this very homogeneous, there's no spatial dependence, and you let that scalar field roll over its very flat part of its potential, then it can give you an accelerated expansion. Okay. So you need a kind of an exotic fluid, which is the scalar fluid, which we call inflaton field. It can give rise to an exponential expansion. Okay. It turns out to be, it can very well be done with a cosmological constant, which we now account them as dark energy. You could have done it with a cosmological constant. If you do with a cosmological constant, what happens is that this H becomes absolutely constant. It will not depend on time. And then it will keep on expanding exponentially forever. You can never get rid of inflation. You cannot enter into more important evolutionary part of the universe like radiation domination and matter domination. So you somehow has to end inflation. Somehow you have to make this H sitting here time dependent, not very time dependent. It should not evolve with time very rapidly, but it should have a tiny time dependence so that at some point of time, it can get rid of this exponential expansion and can now start your decelerated expansion. Okay, that can be achieved by this slowly rolling scalar field. What happens that it actually behaves like a cosmological constant when this is on a flat part of this potential. What happens when it is on the flat part of the potential? So what is the energy density of a scalar field? It will have kinetic energy density. It will have potential energy density. If it is very slowly rolling, the kinetic energy is very smaller than its potential energy. Okay, so most of the universe is dominated by this potential energy of the scalar field. But the moment it gets into this sharp slope of this potential, its kinetic energy will increase. It will now start to roll faster. The moment it starts to roll faster, you will get kinetic energy dominated over your potential energy, and that will kill this exponential expansion. I'll come back to this point again later. Okay. So for inflation to happen, you first of all need a very flat part where the universe would look like that as if it has a constant Hubble parameter like a de Sitter space. So for this flatness to be accounted for, you encounter two slow roll parameters. Epsilon v is the first derivative of the slope and eta v is the second derivative of the slope, and both has to be much smaller than 1. Okay? Because this potential is very flat. Okay? So you need these slow roll parameters to be much smaller than 1 for inflation to happen. And for inflation to end, if you see that if the slope becomes much greater than 1, this epsilon parameter will become 1. So when this epsilon parameter becomes 1, according to this plot, then you will end inflation. This is the standard picture of inflation, which from now onwards I will refer to as cold inflation. Cold inflation is very good. It can predict all that red line fitting CMB, everything is fine. Okay. But you can see it requires a scalar field with a very particular feature. First of all, it has to be very flat. Then it has to have a very large slope. Not only that, it has to have such a bottom of the potential. Why it is needed? Because it is exponentially expanding, right? If you expand exponentially, if even before there is some energy density before inflation started, all these energy densities will exponentially dilute away. You can gracefully exit from this exponential expansion by letting your kinetic energy dominate over the potential energy density. But it will gracefully exit into what? It will gracefully exit into a universe which is devoid of everything. There's nothing. So you have to again reheat the universe. You have to again regenerate the radiation because you cannot enter a radiation dominated era. Because inflation has, by exponentially expanding everything, it has almost diluted away everything. So it's gracefully exiting, but it's gracefully exiting into nothingness. You have to create your universe again. This creating of the matter in the universe is called reheating. And for reheating, you need such a oscillating bottom of a potential where the inflaton field will oscillate, and while oscillating, it will dissipate all its energy to the radiation part. So this picture is very nice, except to me now, I mean, I'm doing inflation since 2006, but when 2018, I started working on warm inflation, I realized that this scenario is very, very constrained. You cannot get rid of this very particular form of the potential. You cannot take any scalar field. Okay? But warm inflation is different. I'll come back.
Comma phi is there a
There's a derivative.
Yeah, the derivative.
This is dB by d phi. This is d2b d phi. Is this water for me?
Yes.
Thank you.
Those were final exam questions in cosmology. Some are sitting at the.
Okay. And these fluctuations that we see in the CMB, inflation can generate that too. Inflaton is basically a quantum field. It has a background field which slow rolls and does all this exponential expansion, but it has quantum fluctuations. But this quantum fluctuations is now dependent on X. These are not homogeneous field. Okay. So these are quantum fluctuations. And as because you, from Einstein's equation, your T mu nu has the scalar field and the T mu nu has fluctuations now. So that will induce fluctuations in your G mu nu. G mu nu is a tensor. T mu nu is just a scalar field, so it only has scalar fluctuations. G mu nu is, on the other hand, is to start with is a tensor. So if you perturb a tensor, you will get all sorts of perturbations like scalar perturbations, vector perturbations, tensor perturbations. Vector perturbations dilute away very quickly during inflation, so we don't bother about that. The scalar fluctuations, on the other hand, induces these fluctuations in CMB that we observe. So that is why I'm saying that this fluctuations is confirmed by inflationary epoch. Okay, and the tensor fluctuations gives rise to your BB modes and the primordial gravitation, which has not been detected yet. But these are called, so inflation always have two divisions. One is called background evolution, which I have shown you in the previous. So these are called this part is called the background analysis of an inflationary phase. You calculate your slow roll parameters and blah blah blah, and then you do the perturbation and then match with your CMB. Okay, so there are two parts which inflationary cosmologist is bothered about. But we will not go into this in perturbation part at all in this talk. What we will do, we will concentrate on the background part. So, as I said, inflation has to end and it has to gracefully exit to a radiation dominated era. Okay, so that's how this graceful exit is there. So, again, if you write down your Friedman, Robertson, Walker, so this is how, if you break down your Einstein field equation with FLRW metric with a perfect fluid, this is how your Einstein field equations will look like. These are called Friedman equations. So this is the energy density. So this is the expansion rate square. This depends on the energy density. However, the acceleration or deceleration will depend on both energy and the pressure. And the pressure is for perfect fluid is also related to energy. So that's why only the energy is there. This omega is coming because there is a pressure was there. So the expansion rate depends on energy density, but whether it is accelerated or decelerated depends on both the energy density and pressure of the perfect fluid. So you can see if you have to, so there is a negative sign sitting here. So if you have to have acceleration for which a double dot should be greater than 0, you need omega less than minus 1/3. Right? Omega less than minus 1/3 is what would give you an accelerated expansion. And lambda, cosmological lambda, is a perfectly fine fluid which can drive inflation. The only problem is that with a cosmological constant, there won't be any graceful exit. You cannot exit from your inflationary phase, as I have already said. However, this is how the energy density and pressure density for a simple scalar field looks like. If you let this is the kinetic term, this is the potential term, and this is the term if the field has any x dependence. So we call it a gradient term. So this, if you let the kinetic term dominate, then what would be your state of parameter? It should be 1, right? So 1 is definitely not less than minus 1/3. There won't be any inflation. On the other hand, if you let the gradient term dominate, you will get a fluid exactly omega phi as minus 1/3, but still it is not less than minus 1/3. So you will not get any acceleration. The only way you can get an acceleration if you let the potential dominate in the energy density. If potential dominates, then you will get a cosmological constant. Okay. Now you have a cosmological constant and the slow roll parameter is much smaller than 1. And so basically slow roll means that the kinetic term is negligible. Whatever is there is the potential energy. And your epsilon v parameter is much smaller than 1. And then inflation ends when your epsilon is of the order of 1. This is the plane scenario. Okay. That means you need the epsilon parameter to be much smaller than 1. But you also need the epsilon to grow for graceful exit. It should have become 1 at some point of time. If you start from 0.001, it should grow and touch 1 unless there is no graceful exit. Right? So this cold inflation requires a kind of potential which is pretty boring. You start with a very small epsilon, let it grow, and once it reaches 1, there is graceful exit. Okay. So you basically need, so this n is called number of epochs, forget about it. This is basically time written in terms of exponential orders because there are exponential expansions, but you just treat this n as time. You need not have to go beyond that. Okay, so you can see that you need an epsilon to be growing. Here epsilon is much smaller than 1, and then suddenly it will grow to 1 and you will end inflation. Okay. So in that sense, basically, this picture is quite boring. But there is a variant scenario, as I said, which I'm interested in, is called warm inflation. What is warm inflation? As I said, that the inflaton was just slowly rolling in cold inflation, and once inflation ends, it dissipates all its energy at the bottom of the potential and it regenerates radiation, and this period is called reheating. That means in this period, we assume that the inflaton is not coupled to any matter. If it is coupled to any other matter, it would have dissipated its energy to that matter. Okay? That is exactly what warm inflation assumes. That you don't assume that the couplings are smaller during inflation. You let them be significant during inflation and let the inflaton field dissipates its energy density to a radiation bar. So during cold inflation, you just have one scalar field, but in warm inflation, you have a scalar field, but also a subdominant radiation bar. This inflaton field is dissipating its energy to the radiation bar, and same amount of energy is being fed into the radiation bar. So what is happening? So the inflaton is trying to maintain a radiation bar. The exponential expansion is trying to dilute away the radiation bar, but inflaton is regenerating radiation and keep maintaining a radiation bar. So what happens? What can happen? It can happen that once one inflation ends, you naturally get the reheating phase. What does it mean? That you don't need such a bottom of the potential. any such potential can work because you don't need an extra reheating phase. Okay, so any such potential, now you're broadening your horizon, right? Now you can accommodate many kinds of scalar potentials, which are now becoming interesting in a inflationary scenario. Okay, so this is why I like warm inflation very much, because now you can play with many potentials. Okay, I don't, how much time do I have?
You have,
5 minutes to
no, you have 13 minutes.
13 minutes. Okay. Okay. So why warm inflation? There are many. One reason I have already told you, this swampland thing. So let me not go into why warm inflation, but let me show you something more interesting. So this is Alan Guth's inflation paper, which was written in 1980. And you can see citation graph. So you can see, so this is in today's day, around 500 papers per year is being written in inflation. 500 papers per year. Okay. So inflation is a very active research field, even after 40 years. Okay. And you can see its citation. Actually, people have stopped citing Guth's paper. So this is not actually a good way of estimating. But still, if you go about it, it has 10, 11, almost 11K citations.
Drop I
That
see.
is this year.
No, this year is not yet completed. This is 2025. This is 2024.
Okay, and that's fine.
Yeah. You just wait. Our new results have come from ACT. This year it will be some 1,000 papers, I'm sure. And you can see what Guth is writing. So Guth is trying, so inflation he was trying to propose because of, to address some of the problems called homogeneity and flatness problem, horizon and flatness problem. But he's writing these problems would disappear if in its early history, the universe super cooled to temperature 28 or more orders of magnitude below the critical temperature of some phase transition. So once this kind of inflation ends, this is super cooling your universe. Okay, that's why I'm referring this as a cold inflation. Okay. On the other hand, after 15 years of Guth, Arjun Berera. So why I like warm inflation? Because it was proposed by an Indian. Okay.
Nationalistic, yeah.
But he's now a UK citizen. He's not, but he is definitely Indian. Okay, he's a Punjabi.
Like most Make in India products, it lives somewhere.
Yes. So it started 15 years after the thing. You can see that the interest is growing. Not as so now nearly 50 to 60 papers are being written per year in warm inflation. The citation is not 4-order digit, but still 3-order digit. But again, you have to account for first 15 years, which the Guth has an advantage of. But anyway, still it is not a bad thing. And you can see that the interest in warm inflation is still growing. Okay. So this is also a very active research field. No doubt about it. And it has good number of citations. How? Now let me tell you why I said that so background analysis is about graceful exit. Okay. So that's why I had background checks for warm inflation. So if you just do the background analysis, you can say a lot about warm inflation. Forget about going into doing perturbations and all. Okay. So in warm inflation, as because there you can see that if I just go back a little, you can see that there is a radiation bar. There is a dissipation term because it's dissipating its energy to this radiation bar. If you, and this, so you can see this is like a harmonic oscillator equation, except there is a
H, dissipation.
dissipation. Okay. This dissipation is due to the expansion of the universe. If you take this term on this side, this will also add to the dissipation, but now dissipating for its energy to the radiation bar. So in warm inflation, you have more dissipation. Dissipation means resistance. Friction. Okay. You have more friction in warm inflation. Okay. So in warm inflation, you write your Friedman equations like this. So Q is a dimensionless parameter, which is just, so there are two dissipative terms. One is due to expansion, one is due to dissipation to its radiation bar. And that Q is the ratio of these two dissipative terms. If the dissipation due to expansion is higher than the dissipation to the radiation bar. This is called weak dissipative warm inflation. And if the dissipation to the radiation bar is higher than the dissipation due to the expansion, it is called strong dissipation. And now, if you write your slow roll parameters, you will see that the inflation will happen when epsilon v is not much smaller than 1. It is much smaller than 1 plus q, and ends when epsilon v is 1 plus q. And you can do this is absolutely a college student can do, a MSc student can do, nothing. I have only written these two differential equations, first order, and you can see how much physics you can. So you can see both epsilon v and q is evolving with time, and these evolutions are proportional to your slow roll parameters. And if you can model your dissipative coefficients in terms of the temperature of the radiation bar and in terms of your inflaton field, and these are the powers of P and C, you can show that warm inflation can be an attractor, blah, 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 or there is a bound on P has to be less than 4. And then you can write it like this. But you can see that both now, what happened in cold inflation? Cold inflation was epsilon v much smaller than 1. So only the left hand side was time dependent. Right hand side was only 1. But here, epsilon v is also changing with time. Q is also changing with time. Not at the same rate. And now graceful exit will be much more colorful. Okay. So how many ways you can end warm inflation? Okay. Let's say you have a scenario where epsilon is constant, just like cosmological constant. There is no graceful exit in cold inflation, but there is a graceful exit in warm inflation. You choose a model for which your Q is decreasing, and once you meet 1 plus Q equal to epsilon, your warm inflation will end. This scenario has no graceful exit in cold inflation, but there is a graceful exit in warm inflation. Okay. If epsilon grows, okay, cold inflation will definitely end. That is the only scenario in which cold inflation will end. But here there are 3 scenarios in which cold inflation can end. If your Q is a constant, epsilon has to match 1 in cold inflation, now it has to match 1 plus Q. You let epsilon grow, at some point of time it will match 1 plus Q and it will end. It is just like cold inflation, but a more elevated condition. But if Q is decreasing, and then also you will end cold warm inflation, right? What happens if Q is increasing, but with a smaller rate? Then also you will get graceful exit. But if your Q is increasing with a faster rate than epsilon, then there is no graceful exit. So epsilon grows is not the only condition in which you can end warm inflation. There can be scenarios where Q is growing faster than epsilon, and even if epsilon is growing, you cannot end warm inflation. Okay. And if Q decreases, again, cold inflation cannot end, but warm inflation can end if your Q is decreasing faster than epsilon. Okay. Great. So epsilon depends on the form of the potential. Your epsilon, the way Q is evolving, depends on both the potential and the choice of your epsilon parameter. So now this graceful exit condition can put constraints on the combinations that you can take of the potentials and the dissipative term. Not all potential and not all dissipative term can lead to graceful exit, as you can see. Okay. So if you just take just this chaotic potentials like this, and if you choose like this, so these white regions are where there won't be any graceful exit. Okay. So this is what I did with Ramos, but is this all that the background analysis will tell you? I can show you I showed you the cases where there will be a graceful exit, but it should be gracefully exit to what? To a radiation band. Does warm inflation always gracefully exit to a radiation bath in warm? Answer is no. Why? Again. So these were the two equation of motions. So this is the evolution of the inflaton field. There is the evolution of the radiation bar. And I said that it's very hard to maintain a constant radiation bar. So I'm just saying that I am producing a constant radiation bar. So radiation, the energy density of the radiation bar is not evolving. So I can just put 0. And then I can write it as, you can take this 4h down. My Q is epsilon by 3h. So that I have written as Q. And kinetic energy is half pi dot square. Okay. And now if you have a scenario where Q is decreasing, you can see this is a factor of order 1. And if Q is decreasing, then rho r is decreasing with respect to your kinetic energy. So it might happen that in this decreasing Q scenarios, you, rather than going into a radiation dominated era, you go into a kination dominated era. And once you go into a kination dominated era, there are fantastic gravitational wave signatures in those eras. So you can actually pinpoint those eras and say that will be a smoking gun test for form inflation. Okay, so this is the work which I am now doing with my PhD student Archana.
Stochastic gravitational wave.
Stochastic gravitational wave.
But same which comes from the inflation.
No.
No,
The peaks are different. The peaks are different. So what I wanted to say is that the background analysis in cold inflation is pretty mundane. कुछ भी नहीं है. But the background analysis of warm inflation is not mundane. Even before you go and do your perturbation theory, your background analysis gives you a lot of information about the model that you have chosen for your analysis. So this background checks for warm inflation is really, really important. Before I end, let me give you a small advertisement of our department. This is our Astro Cosmo group from Ashoka. They are all big names. Dipankar Bhattacharya, Shomogra Chaudhary, Professor Kandu, they are all big names. Dipankar is master in neutron stars. Shomogra is both in Astro and Cosmo. And Kandu is, of course, worldwide his student, his supervisor. He is a world-renowned physicist for magnetic fields in astrophysics, and this is a much thinner and younger version of me. And I do, as you have seen, what I have done. I am doing inflation, and there are other areas which I do not think is maybe interesting for this audience, but there is condensed matter and biophysics. We have Shomen Bhattacharya, Gautam Menon, both are well-known, internationally well-known names, and there are junior faculties like Pramoda and Garima. There's quantum field theory and memory theory, kind of also string theory done by Amin Nizami. If you are interested, please apply to our PhD program. Thank you.
Okay, questions? Yes, sorry.
Considering our bodies and the whole space, they are constantly in one direction.
No, it doesn't start at one space. Inflation doesn't start at one space. Okay, if you go back to old ages, there is something called bubble nucleation. So within one bubble, the inflation will start to end, the other bubbles will collapse. So the bubble which is inflating will now encompass our whole universe. So it is not happening at one place. It is happening, whatever the visual universe we are seeing today, if all the space at one time had started expanding.
Whichever direction we
Yes, it doesn't destroy the homogeneity, the cosmological principle.
then won't there be many points of the source? All direction will have one.
No, this is like a space field with this scalar field whose potential is dominant. And the whole space started to inflate. Okay. It's not just one part.
And the space itself will start to inflate.
Yes, that's a scale factor. So even in the expansion, in Big Bang theory, it's a space which is expanding.
That's what's dominating the metric, the mean post.
That is dominating the metric, the exponential.
The effect.
Effect.
Other questions for everyone?
Yes.
I had many, but I can't remember only one right now. It was a great talk, lot of things. As you said that cosmological constant would not be a viable potential for inflation. But now again, the new data is suggesting that cosmological constant might not be
Dark energy either.
yeah,
W
So-
is not -1 necessarily.
Necessarily. Yeah.
So are there
So there are quintessence models. So similar like inflation, there are scalar field models for dark energy called quintessence model. People do analyze those quintessence models for dark energy as well.
So is in that case, is that just one single scalar field going through, evolving throughout the history of the universe?
So people have tried to unify inflation and the dark energy. It's very natural to assume that there are no many scalar fields that we know of. There is only one scalar field which is Higgs. It can neither be inflaton, it can neither be the dark energy. There are reasons for that. Okay. So how, I mean, of course, whatever field you have to extend your standard model and fit them into it. So if you have a minimal extension where one field can accommodate both the early time expansion, acceleration and the late time acceleration, that is the best. So many people have tried unifying, but somehow then the inflaton field should not decay fully and there should be some remnant of that inflaton field which can later on behave like a dark energy. Okay, so people have tried that. Yes.
Other questions? Devasita?
You have said that this bubble thing is now gone.
It is gone, yes.
Then if heat system is inflation,
Inflection.
yeah, sorry, inflaton. Then when the phase transition or not phase transition, phase transition is occurring. You must know the time when the metastable.
Yes, yes, yes.
That the bubble thing works, right? That thing, the
That
bubble is a.
it works.
Yes.
People have worked, when people do work on Higgs inflation, for Higgs to behave like an inflaton field, you have to have a very large coupling with the gravity. That is a Higgs inflation field. So now it's not a minimalistic standard field, a standard model. Now you have to bring in gravity into it. And then you have to couple very strongly. The coupling is 10 to the power 3 or 4.
Oh.
With that, yeah. That is what comes in.
Okay, yes, ma'am.
So yeah, my question is kind of related to both DM and Onitvan. And also the other Onitvan who spoke last week. So we were hearing this Higgs boson talk last week in our colloquium. And Professor Kundu ends his talk by saying that there are indications that the Higgs sector is not a single scalar field Higgs. It's a multi-scalar Higgs sector. There are some indications of that, and there are some possible mass scales that are coming up, even in the LHC data. So, in the scenario for inflation, because whatever we spoke here, I think is related to just a single field inflation. What is the status in the inflation field where we discuss about multiple inflation?
So the thing is that if you have multi-scalar fields driving inflation, so there won't be this only one TT spectrum. This is called the adiabatic spectrum. There will be further spectrum called isocurvature spectrum. But Planck has put a very stringent bound on, even if your whole theory has multiple scalar fields, somehow they will conspire and will let only one field to drive that influence. Even if it's a one out of many fields, or all the fields will combine in such a way that they will behave like one single state. Otherwise, you will produce a lot of isocurvature perturbations, and then that's not what Planck is saying in this time. There's a very stringent bound on. Because if you go to string theory has many scalars. I mean, they are just full of scalar fields. They just live in a pool of scalar fields. So if you have string theory models of inflation, multi-field is a more natural way. But again, somehow you have to convert it to a single.
Is it sir?
So,
As I understand that